Ever considered why we never come across half an electron in nature, or why the charge on that electron always seems to be of a fixed amount, an unchanging constant? Have you ever thought about why, amidst the vast orchestration of existence conducted by the rigorous laws of physics and the unpredictable whims of chance, no particle has been observed that carries a half charge? These are not just idle musings, but questions that have captured the curiosity of great minds for centuries, and invite us to step into the fascinating realm of charge quantization. In today's discussion, we're going to delve deep into this extraordinary phenomenon, navigating through its complex undercurrents and decoding its profound implications. The principle of charge quantization is not merely a chance encounter or a casual deviation. It is an essential principle that forms the very warp and weft of the universe's cosmic tapestry. In the grand scheme of things, it is foundational, not incidental, a constant, not a variable. Picture a universe where every charge is an integral multiple of a basic unit, much akin to the way we use integers in our daily count. We do not state there are 2.5 individuals in the room or claim possession of 3.7 apples. No, we always operate with whole numbers. This analogy provides us with a basic understanding of the core essence of charge quantization. At the epicenter of particle physics, charge quantization holds its prime position. It declares with undeniable certainty that the charge of any particle must be an integral multiple of what we call the elementary charge. This elementary charge is the charge harbored by an electron or a proton. This principle emerges as a steadfast law, an unbroken decree of physics. Nevertheless, as with all great enigmas, this glaring fact propels us to yet another question. Why do charges come quantized? The answer to this question plunges us into a universe so minuscule that it challenges our comprehension, the intriguing world of quantum mechanics. Quantum mechanics, an offshoot of, grapples with particles so tiny that they confound our understanding. It introduces us to an alternate reality where particles can be present in two places simultaneously, and felines can exist in a state that is both dead and alive. In this quantum realm, certain properties of minuscule particles, including charge, are found to exist in distinct quantized units. Just like the steps on a staircase, you can position yourself on one step or the next, but never in between. This unique characteristic of quantum mechanics is not just a figment of theoretical imagination. It has been substantiated by innumerable experiments and stands today as a cornerstone of our current understanding of the cosmos. This analogy of the staircase, which beautifully embodies the paradoxical and counterintuitive nature of charge quantization, may appear remote from our usual experiences. However, it is this very realm that forms the bedrock of every visible and tangible thing in our world. It is this principle of quantization that governs the very heart of our physical reality. Robert Millikan, the renowned physicist, graced the scientific world with a radical idea in the early 20th century, the notion of charge quantization. This concept didn't just emerge out of the blue, it was the fruit of a groundbreaking experiment carried out by Millikan himself, famously known as the oil drop experiment. Millikan, in this experiment, meticulously examined charged droplets of oil that were suspended between two metal plates. His painstaking attention to detail and rigorous examination led to a revolutionary revelation. Charge isn't just some random continuous variable. On the contrary, it was found to always be a multiple of a specific, fundamental unit. Millikan's oil drop experiment thus became a cornerstone in the field of quantum mechanics, marking a significant milestone by providing a concrete foundation to the quantized nature of physical quantities. This elementary unit of electric charge, named as the elementary charge, is not just an ordinary value. It's a fundamental constant of nature with a value of approximately 1.6 times 10 to the negative 19th power coulombs. This value may seem insignificantly small, but its implications reverberate across both the microscopic and macroscopic worlds. The principle of charge quantization, introduced by Millikan, holds colossal importance in the atomic world. It explicitly dictates the charge of the electrons. The negatively charged particles in an atom is quantized. This concept perfectly complements the quantized energy levels of the electrons. The energy levels they reside at are not random or arbitrary, but rather specific, and the principle of charge quantization, electrons would be unbound, free to move in a non-specific, unregulated manner. They would not be confined to their energy levels and would not be able to orbit around the nucleus in stable, discrete energy levels. This would lead to catastrophic anomalies in atomic structures, creating chaotic and unpredictable universe. Let us pause for a moment to fully appreciate the importance of Millikan's contribution and the principle of charge quantization. Without it, the structure of atoms, which form the basis of all matter, would be in utter disarray. Electrons would not be able to maintain their stable orbits around the nucleus, leading to a volatile, chaotic, and entirely unpredictable universe. In essence, the world as we know it wouldn't exist without Millikan's revolutionary discovery. Now let's delve deeper into the captivating twist in the tale of charge quantization. For those unacquainted, charge quantization is a principle where charge always appears as a multiple of a fundamental unit, called the elementary charge. This principle is upheld unflinchingly by the laws of quantum mechanics, which allow certain particle properties to exist only in specific amounts. While this holds true for almost all matter, there are intriguing exceptions, and this is where the story gets interesting. We invite you into the enigmatic world of quarks, these peculiar particles that carry fractional charges. But what makes their existence even more fascinating is their disobedience and adherence to the principle of charge quantization at the same time. These particles, carrying partial charges, are never found alone. They adhere to the principle of charge quantization by combining to form particles with integral. This unique characteristic of quarks takes us on a journey of understanding charge quantization from an atomic level to the very fundamental nature of matter itself. The discovery of charge quantization has far-reaching implications, from the stability of our universe to the structure of atoms. Unraveling this principle is like peeling back the layers of our universe. It might seem like a simple principle, but every nuance it offers provides profound into our universe. It's a principle that highlights the elegance of physics, where every particle, no matter how small, adheres to mesmerizing laws. So keep asking, keep exploring, and keep uncovering the wonders of the physical. After all, every extraordinary discovery begins with a question. In this segment, we will explore the current research and future implications of charge quantization. As we continue to probe deeper into the realm of quantum mechanics, we are constantly discovering new facets of charge quantization. Current research is heavily focused on understanding the behaviors of quarks in extreme conditions, like those found in neutron stars or in the aftermath of the Big Bang. The findings from these studies could drastically alter our understanding of the universe and open up new possibilities for technological advancements. Moreover, the future implications of charge quantization are vast and varied. One of the most exciting prospects is the potential to harness the power of quarks for energy generation. Imagine a future where we could use quarks to power our cities, vehicles, and even our homes. On a more fundamental level, the ongoing research into charge quantization could lead to a unified theory of physics, bridging the gap between quantum mechanics and general relativity, two of the most successful yet incompatible theories in physics. As we delve deeper into the mysteries of charge quantization, we can only imagine what new doors will be opened, what new realities we will uncover. Stay tuned as we continue to explore the fascinating world of charge quantization.